Hi students, this is a lecture about section 14.5, which is about gradient vectors. This is Max, he's my cat, you've already seen him before. The gradient vector of a function f of x comma y comma z is written as gradient of f, which looks like an upside down triangle, sometimes called delta. And so gradient of f, actually it might be called del, come to think of it. I think it's called del, not delta. I think delta is where it's a right side up triangle. But anyway, del of f equals partial f partial x times I plus partial f partial y times j plus partial f partial z times k. So it's actually a vector function. It has three components, and each component is actually the partial derivative of the function in that direction. And these gradient vectors are used a lot in places like physics for directional derivatives, which is the next topic we'll be learning about in the next video. Okay, so the gradient vector is just a bunch of partial derivatives, and each partial derivative is multiplied times a unit vector. So because these are long, I think I'm just going to do one of them. I'm going to try to do one of the hardest ones from your homework so you can see all the tricks. Okay, so example. Find the gradient. So del f at the given point. Okay, find del f at the given point. All right, and they're telling us that our function f of x comma y comma z is equal to e to the x plus y times cosine of z plus the quantity y plus 6 times sine inverse of x. Okay, and then the point they're giving us a point which is 0, 0, pi over 2. So at the end of this problem, after we found the gradient of f, we're going to be plugging in x, y, and z for this point. So the point 0, 0, pi over 2. Okay? But first we're going to just find gradient of f, because that's the hard part. Okay. So to find gradient of f, remember I just said that the formula is partial f partial x times I plus partial f partial y times j plus partial f partial z times k. So we're going to start by finding each of these partial derivatives. Partial f partial x, partial f partial y, and partial f partial z. Okay, so let's start with partial f partial x. So for partial f partial x, remember that means the other variables are constant. So that means y and z are constant. Y and z are both constant. Okay? So for partial f partial x, we have these two terms. For the first term, since y and z are constant, the only thing we're really taking the derivative of here is e to the x plus y. The rest of this is just constant, so we don't care about it. It just stays along for the ride. Okay, so we're going to have the derivative of e to the x plus y is still e to the x plus y. But then we have to use the chain rule, so we have to multiply this times the derivative of x plus y. And remember, since y is a constant, the derivative of a constant is 0. And then the derivative of x is 1. So it's really e to the x plus y times 1. But then we still have a cosine of z. Okay? So there we used the chain rule, but we didn't end up really needing to use it since the derivative of x plus y is just 1. And then for the second term, y and z are constant, but x is not a constant. So the y plus 6 is constant, but sine inverse of x is not constant. And if you don't remember the derivative of sine inverse of x, you can always go into the formula sheet that I have in one of the modules. The formulas from Calc 1 and Calc 2. And like if I go down here, the derivative of sine inverse is 1 over the square root of 1 minus u squared du dx. So 1 over the square root of 1 minus u squared. So here we're going to have y plus 6 times 1 over the square root of 1 minus u squared. Well, here u is just x. 1 over the square root of 1 minus x squared. And because it's just x, we don't have to use the chain rule. So we don't have to write times du dx. So literally all I did was I went down on the formula sheet on the first page right here, where it has d dx of sine inverse is 1 over the square root of 1 minus u squared. Okay, cool. So, we're good there. So that's our partial f, partial x. And there's not really much to simplify here. I'll just erase the 1 since we don't need that. So that's e to the x plus y times cosine of z. Okay, so now we've got our partial f, partial x. So for our next one, let's take a look at partial f, partial y. Okay, so for partial f, partial y, that means the other two variables are constant. So that means x and z are constant. Okay, x and z are constant. Okay, so for partial f, partial y, since x and z are constant, that means for e to the x plus y, the derivative of that is just going to once again be e to the x plus y, and then the cosine of z is constant. So this first term is still going to be e to the x plus y times cosine of z. Right, because the derivative of e to the x plus y is going to be e to the x plus y times 1. But if it's 1, we don't need to write it. And then cosine of z is constant since z is constant. So this first term is just going to be e to the x plus y times cosine of z. Okay? And then for the next term, y plus 6 times sine inverse of x. We know that x and z are constant, which means that we only really have to take the derivative of y here. So the derivative of y plus 6 is just going to be 1. But we still have a sine inverse of x, so we have 1 times sine inverse of x. Okay, so we have plus 1 times sine inverse of x. Since the derivative of y plus 6 with respect to y is 1. But then we don't need to write this 1 because any number times 1 is the number. Okay, so now we have our partial f, partial y, which is e to the x plus y times cosine of z plus sine inverse of x. Okay? And then our last derivative that we need to calculate is partial f, partial z. So let's do that one. Okay, so partial f, partial z. For this one, once again, the other variables are constant for a partial derivative. So here, x and y are constant. X and y are constant. Okay, so let's start with the e to the x plus y cosine of z. Since x and y are constant, that means e to the x plus y is constant. So here we don't really even worry about the e to the x plus y, it just stays along for the ride. And then the derivative of cosine of z is negative sine of z. So this is going to stay the same, and the cosine of z becomes negative sine of z. So we're going to have e to the x plus y times negative sine of z, or negative e to the x plus y times sine of z. Okay, literally all we took the derivative of was the cosine of z, because that was the only part that wasn't constant. Okay, and then for the second term, we have an interesting situation. So we know that x and y are both constant, and so that means sine inverse of x is constant, and it also means y plus 6 is constant. So this entire thing here is constant. So this whole thing is constant. And what's the derivative of a constant? 0. Okay? So this whole thing, when you take the derivative of it, it's just 0. So actually for partial f partial z, we have this whole thing plus 0. Okay, but obviously we don't have to write plus 0, so we just erase that. And so our partial f partial z is negative e to the x plus y times sine of z. Okay, so now that we have the three partial derivatives, now we're ready to go ahead and write down the gradient. So what's the formula for the gradient? Well, gradient of f, or del f, equals partial f partial x times I plus partial f partial y times j plus partial f partial z times k. Right, so three components. And we know partial f partial x, partial f partial y, and partial f partial z. But really what we want to do is, before we plug all these in, we actually want to evaluate each of the derivatives at the point they gave us. And the point that they gave us here was 0, 0, pi over 2. Okay, so we want to evaluate each of these derivatives at 0, 0, pi over 2. So we're actually going to do that for this entire right side here. We're going to evaluate all of those at 0, 0, pi over 2. And remember, that's a point of the form x, y, z. Okay, so let's start with partial f partial x. So if I evaluate partial f partial x at 0, 0, pi over 2, let me go ahead and do that over here. Evaluate it at 0, 0, pi over 2. So that's going to actually equal, we're just going to plug in x is 0, y is 0, and z is pi over 2. So we're going to get e to the 0 plus 0 times cosine of pi over 2 plus 0 plus 6, right? So plus 0 plus 6 times 1 over the square root of 1 minus 0 squared. So as you can see there, we're just plugging in 0, 0, and pi over 2 for x, y, and z, which is pretty easy. So e to the 0 is 1, so that's just 1. 0 plus 6 is just 6. And the square root of 1 minus 0 squared is just 1. So here, for the partial f partial x, we actually just end up with cosine of pi over 2 plus 6. Now cosine of pi over 2 is the same as cosine of 90 degrees, and it's the x-coordinate. So we know that the x-coordinate for cosine at 90 degrees is actually 0. So cosine of pi over 2 is 0. So this first term is 0. So this first derivative is actually just going to be 6. Okay? All right, cool. So, and then we have to plug in for the other two derivatives. So for the next one, we're going to find partial f partial y, evaluate it at the same point, evaluate it at 0, 0, pi over 2. Okay, so again, we plug everything in, and we get e to the 0 plus 0, e to the 0 plus 0 times cosine of pi over 2. And then we have plus sine inverse of 0. Okay. So e to the 0 plus 0 is once again just 1. And cosine of pi over 2 is actually 0, right? Because it's at 90 degrees on the unit circle. And then sine inverse of 0 you might not remember, but it's actually the same as the angle. Well, it's really the y-coordinate. Sorry, it's the angle when the y-coordinate is 0. So your y-coordinate is 0 when your angle is 0, or 2 pi. But sine inverse of 0 isn't defined for 2 pi, it's only defined for 0. So sine inverse of 0 is 0. So really here we have 0 plus 0. 0 plus 0 is 0. So this coordinate is 0. Okay, so partial f, partial y, evaluated at 0, 0, pi over 2 is just 0. And then for our last coordinate, for partial f, partial z, if we evaluate this one at 0, 0, pi over 2, once again, plugging everything in, we get negative e to the 0 plus 0 times sine of pi over 2. But remember that sine of pi over 2 is actually the y-coordinate on the unit circle when you're at 90 degrees. And the y-coordinate there is actually 1. Okay, so we're going to have negative of 1 times 1, which is negative 1. Okay, so the second coordinate is negative 1. Sorry, not second coordinate. Third coordinate is negative 1. Okay, so what we've got here is 6, 0, and negative 1. And that's going to be our first, second, and third coordinate. So for our answer, we have 6i plus 0j minus 1k. That's what we said, right? 6, 0, and negative 1. Okay? And then remember, if you have something like 0j, you can leave it as 0j, but the standard thing to write is if you have anything times 0, you don't write it in your answer. Okay, so most people would just not write the 0j. So they would just write 6i minus 1k, but once again, you don't write the 1, so you just write 6i minus k. 6i minus k. Okay, and that's our answer.